Okay, this is number 2, page 71. On July 1st, 2012, you deposit $1,000 into an account that pays 6% interest annually. How much is it worth on July 1st of 2032? Before you turn your calculator on, write a calculator-ready expression. So, how would you do this problem? So you're taking $1,000 and you're depositing it into an account, and then 20 years later, you want to see how much it's worth. Yes?
1,000 times 1.06 to the 20th power.
Good. So 1,000 times 1.06 to the 20th power. Okay. You can plug that in, get an answer, right? Good. Okay, here's a continuation of number 2. On number 3, it says, on July 1st, 2013, you deposit $1,000 into an account that pays 6% interest. And you want to know how much this investment is worth on July 1st, 2032. So it's pretty related to the last question. What would that look like? Someone different. Samantha. Okay. Right. So now you're taking another $1,000. So it's a completely separate deal. You're putting $1,000 into a different account, let's say, for right now. So you just do 1,000 times 1.06, but now it's 19 years. Okay, and now they're saying, well, what if they were all the same account, and you're depositing them in there, or they're not the same account, but if you kept on doing that every year, so this is 2013, then 2014, you're going to be, that amount is going to be deposited, 1,000, and now it's only going to be in there for 18 years. And then 2015, same thing's going to happen, but that's only going to be in there for 17 years. And you can keep on doing this forever. So I guess the goal is, and probably going to see in the next problem, is now instead of making one deposit and putting it in there for 20 years, now we're doing multiple deposits, the same amount of deposits. So you're doing the same $1,000 every year, okay, until the 20 years is up. So continuation from the last one. Here's the idea. We're depositing $1,000 every year for 20 years, okay? And we want to calculate how much all of these would be worth with the interest 20 years later. So it says rather than getting the answer tediously by adding the results of 21 separate calculations, we can find a shorter way. So if you think about it, here's what's going to happen. The very first moment that we enter, we're going to put money in, right? That's going to be times 0. So after 20 years, that is going to be our amount we have for that one. Then the next year we put in for 19. And we keep on doing this until we get to the 20th year. Well, in the 20th year, we're going to put in the $1,000, but we're done. That's the last 1,000 we put in. It's been 20 years now. So we put that $1,000 in. That's why this expression right here is here, because if I put $1,000 in, it had 0 time to mature. That was just an extra $1,000 I'd add to the top. So this would show the total amount that's going to be in the account. So now it's saying, obtain a second equation, and this is where the tricky part. We don't want to do this. We don't want to do this and have to add it out the whole time. It'd be nice if there's a shortcut or a formula for doing this kind of calculation, especially if we're going to do it for 50 years or for 100 years. So what it's saying is to obtain a second equation by multiplying both sides of this one by 1.06. So if I multiply this by 1.06, again, I'm doing like 1.06 times that side, and then 1.06 times that side. What we end up getting is 1.06v Now, when I multiply this first, I have to distribute this, right? So this has to be distributed by every term here. okay? If I distribute the 1.06 times this first term, what would I end up with? What would my term look like? I'd have 1,000, right? I'd still have 1,000 times. What's the only thing that's going to change there? The 1.06. I'm multiplying this. Since I'm multiplying,
Up to the end?
well, I'm only multiplying by 1, right?
Right.
And it was a 0. So I'm adding an exponent there of 1. So again, if I multiply this 1.06 out here times this, these are multiplied together, that 1.06 just changes to the exponent of 1. So what's this one going to change to?
2.
2. Run out of room here, so I don't want to run out of room. So now, at this point, this is going to go on forever, right? Dot, 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 dot. And what's my last term going to be? 1,000 times 1.06 to what power? 21. 21st power. That makes sense? Okay. And then it's going to say, I want to combine these two. Well, the best way to combine stuff is usually to either add them or subtract them. I want to solve for v. So if I rewrote this, the original one, I'd have v equals 1,000 times 1.06 to the 0 power plus 1,000 times 1.06 to the first power. That's going to go on forever until I get to 1,000 times 1.06 to the 20th power. I want to subtract these. What's going to end up on the left side there?
1.06.
Not 1.06. 0.06. That's going to be 0.06 v. Okay. Again, I'm subtracting them because I want to combine these. And what I'm noticing here, and hopefully you guys are noticing this too, those are equal, right? I'm going to have a bunch of these that are equal. That makes sense? And if I subtract them, what's going to happen to those equal terms? They're going to cancel out. So when I subtract these here, this 1,000, 1.06 minus 1,000, 1.06 to the first power, that's going to go on forever. What's the last term that's going to be canceled?
20.
The 20th power. So this is going to be canceled for the one that's before here, right? So now all that we have left
Is the 21st?
is the 1,000 times 1.06 to the 21st power. And then what's left from the bottom one? To the 0 power. We subtracted it, so it's going to be minus 1,000 to the 1.06 to the 0 power. Now, if I want to solve for v, what do I divide by? 0.06. Now, I'm not going to say that this is an easy, compact way to write it, but that is definitely easier to write this than it is to write 20 different terms out, or 21 different terms. So that's our shortcut right there. And we're going to hopefully use that shortcut later on. Okay, so this is taking what we just learned about the interest rate problems and extending it a little more. It says there are two examples, pretty much, of a geometric series. So let's look at example 1 here. I have 16 plus 24 plus 36 plus 54. That is easy enough to type in your calculator and get an answer to. But again, the idea is, if we have this formula we can use, why not check the formula on an easy one and see if it works? So first of all, what's a geometric sequence? What does that mean we're doing? Multiplying everything by something, right? So in this series here, we go from 16 to 24. What are you multiplying the 16 by to the 24? 1.5. So if I were to write this out, you could say that I would take 16 plus 16 times 1.5 to the first power, right? Because if I take 16 times 1.5, I get 24. And this would be 16 times 1.5 to the second. And this would be 16 times 1.5 to the third. So if we go back to what we just did, we're just going to check to make sure this works. We took this last one, right? This last term right here, and we added up a exponent. So we went 16 times 1.5 to the fourth minus the first term, which was just 16 to the 0, which is just 16, right?
Yep.
Divided by what? 0.5. Someone with the calculator, see what that is, please?
I got it.
All right, I'm using that. So Connor says we have 130 is our answer. If you add all these up together, you get 90 plus 40, which is 130. So see how that is our, not quicker way for this problem, but in general, that's going to be a quicker way to add a geometric series. So here, that is easy to do, but if we go to this next one, oh, it already tells us our sum is 130. Look at that. I didn't even read that far. Okay, so let's look at the second example they give us. Our second example is you have 32 plus a negative 16 plus 8 plus a negative 4 all the way down to plus 0.125. All right, let's come up with the equation here. The first one is 32. That means the second one has to be
-1/2.
right, so 32 times -1/2 to the first power. And at this point, you should be going, okay, I see the pattern. It's going to go out 9 terms. We have to be a little careful here. So it's 9 terms. So what's going to be my power on the very last term?
10.
I got 8 and I got 10. Which one?
Oh, there's 9 terms, so 10.
Well, I'm just saying what power's on this last one? 8. Because think about this. I got 9 terms. I started at 0.
Oh.
So that would go out 9 terms. Okay? Now, if we want to calculate the sum of all these, we could just do what we've been doing. 32 times -1/2 to the 9. Notice that's how many terms we have. 9 minus 32. That's our first term. Divided by, ooh, it's going to be tricky. We have -1/2 there.
Would be 0.25.
So let's freeze for a second. What we've been doing is we've just been looking at that right there, which has been 1.5 minus 1.
So
Right?
Yeah, so if it was 0.5 minus 1, it would be -0.5 then?
So it'd be -1/2 minus 1. That makes sense? So you take your rate that's in the parentheses here, you subtract 1 from it, and that's what goes down here. In the previous problem, it was 1.06 minus 1. So now we're going to use -1/2, because that's in parentheses, that's our multiplier, minus 1. And someone use that calculator and just double check that you should get 21.375. Is that what we get?
Yep.
21.375.